to the second part of two-dimensional discrete Fourier transform. So now let's start with image filtering. So now in image processing, when you get an image, if there is noise present in it, the quality of the image decreases. Also, the image analysis can be affected severely. This is why image filtering is done. Image filtering, what it does is that it emphasizes the edges and it removes all the noises and the impurities and makes the image more clear and better in quality. Most of these methods operate on each pixel separately. What filters do is that they take up pixels value and they compare it with the neighboring pixels and make them better basically. So now if you see, this is the first image, this is the first original image, and these three images are the ones which have filters applied to them. So as you can see in this image, the quality has increased a lot and is much more clear. In fact, more clear than the original image. Now there are two complementary ways of studying linear filters, which is in the spatial and the frequency domain, which we did earlier. So now let's see about filtering images in the frequency domain. So now we can represent it as a sum of many sine waves of different frequencies, amplitudes and direction. That is the frequency domain. The greatest advantage of the frequency domain is that one can manipulate the spatial frequency components easily, as I said before. Now frequency domain filtering is attractive compared to spatial domain filtering because fewer computations are involved. Like I said before, frequency domain in the calculation of frequency domain is very much easier than spatial domain. That's why the frequency domain filtering is also easier as compared to the spatial domain. The other advantages of filtering images in the frequency domain rather than the spatial domain is that we get extra insight into the image. The calculation becomes much faster using the fast Fourier transform, and there are much more new filters that are available. So now this is the algorithm for the frequency domain filtering. So now let's consider f of xy to be the original image in which frequency filtering is required, and then we obtain the Fourier transform of the image. Then we read the spectrum and multiply it by minus 1 raised to x plus y, where x plus y is the coordinates, and we multiply this to the center of the transform. Then we design a frequency domain matrix function, which is h of xy, and which is basically like a mask. The shape of the mask can be a circle, rectangle or any shape depending upon the requirement of your application. Then we design or we obtain the Fourier spectrum of h of xy to get h of uv. Then we multiply the Fourier spectrum of the filter with the Fourier spectrum of the image, and we get g of uv, which is equal to h of uv into f of uv, which is the Fourier spectrum into the Fourier spectrum of the filter, which is h of uv, into Fourier spectrum of the image, which is f of uv, and we get g of uv, which is the filter output in the frequency domain. Once this is obtained, we apply inverse Fourier transform to get the original image in the spatial domain. Once IFT, which is inverse Fourier transform, is applied, we extract the real components. Like I said before, frequency domain is basically like an equation in the complex form, which is x plus I y or something. So we extract only the real components and multiply it by minus 1 of raised to x plus y, which is used to offset the effect which we did in step 1. Once this is done, we display the image and the filtering is done in this step. Let's see the different types of frequency domain filters. Now there are two types, one is low pass and one is high pass. The low pass is the smoothing one and the high pass is the sharpening one. There are three types in both of them, which is ideal low pass, Butterworth and Gaussian, and same in sharpening. Now in smoothing, a low pass filter that attenuates, which is suppresses high frequencies while passing the low frequencies, and it creates a blurred, which is smooth image. It leaves the lower frequencies unchanged and ignores the high frequency noise components. This is like a very easy type of filter. What it does is it suppresses high frequency and passes the low frequency. So the low frequency is kept as it is and ignores the high frequency noise components. This is how smoothing filtering is done. Now sharpening of an image in the frequency domain can be achieved by high pass filtering process, which suppresses low frequency and it doesn't disturb the high frequency, which is the reverse of smoothing. So now High pass filter is given by h of HP and low pass filter is given h of LP. And we can say that for a particular point, high pass filter, which is h of HP of UV, can be given by 1 minus h of LP of UV. Moving on. So now these are the different formulas which is used to calculate the LPF and the HPF of three different types of both the filters. These are the formulas for the ideal LPF and the HPF respectively. This is for the Butterworth LPF and HPF. This is for the Gaussian LPF and HPF. So now this is the original image and this is the Fourier transform of the image. And these different 1, 2, 3, 4, 5, 6. These 6 images are the results of different filters. It's the ideal low pass, Butterworth low pass, Gaussian low pass, ideal high pass, Butterworth high pass and Gaussian high pass. These 6 images are the results, which is the final output, by applying each filter to the original image. Now let's see what is homomorphic filtering. Homomorphic filtering is a generalized technique for signal and image processing. It involves a non-linear mapping to different domain in which the linear filter techniques are applied, followed by mapping back to the original domain. Homomorphic filters is generally or sometimes used for image enhancement. To enhance images, of course, the illumination become more better, and so the high frequency components are increased and the low frequency are reduced, which is basically like a high pass filter. So if you use an image and apply homomorphic filter on it, and you take an image and apply high pass filter and then homomorphic filter on it, then the result of the second one becomes better than the original, whereas the result of the first one becomes at par with the original. So obviously using the homomorphic filter after using the high pass filter makes the image much more better. Homomorphic filtering is used for improving the appearance of a grayscale image by simultaneously intensity range compression, which is illustration, and contrast enhancement, which is reflection. So now m of xy can be given as I of xy into r of xy, where m is the image, I is the illumination, and r is the reflectance. So we have to transform the equation into frequency domain, obviously, to apply the high pass filter. So now it is very difficult to do the calculation after applying Fourier transformation because it's not a product equation. So therefore we have to use log. So your ln is your log. So if we see this equation, which is m of x of y is equal to I x of y into r x of y. Once you apply log on both sides, you get log of m of x of y is equal to log of I of x of y plus log of r of x of y. This is by using the log property, which you know by doing maths. Then we apply the Fourier transform on it, and then we apply the high pass filter. So after applying the high pass filter, your output will be n of uv will be h of uv into m of uv, where h will be any high pass filter, which can be Gaussian, ideal or Butterworth, and n will be the filtered image in the frequency domain. Once this is done, you perform inverse transform on it to get your final result. So now consider this example. This is the original image, which you can see is not so clear. This and the image on the extreme right is by applying only a high pass filter. So you can see that the last image is not very clear, whereas in the middle image, this one is after applying the high pass filter and the homomorphic filter. Like I said before, if we use the homomorphic filter and the high pass filter together, the image becomes much more clear and better in quality than the original image, as we can see over here. So we can see that homomorphic filtering is used for correcting non-uniform illumination. So you can see the illumination has become much better and the image has become clearer than the original image. It is used for log spectral domain to separate filter effects from excitation effects, or for computation of the spectrum as a sound representation. So homomorphic filters also not only used for images but also for sound. So it can be used in the log spectral domain, can improve sound intelligibility, which is used in hearing aids. Thank you for learning with Junk Minds. I hope you like this chapter.